It is a beautiful, by my standards at least, Monday morning, and we are into a new block. We have GR2 behind us for most of us. We do. I know there are still some of you, and I say you in the larger 356. I don't know if it applies to anyone in this actual section, but we have some makeups that we have to do. But with GR2 and Block 2 behind us, I believe we are approximately, we've got just a little under half of the points in the course left. And so I will be kind of talking with some of you guys later on kind of the road forward. I will bring up, because some of you guys asked me this before class, here's a quick and dirty summary of statistics for our GR. So the top is a histograms of GR1 and 2, whereas the bottom is a box plot of the scores by section. Now, the histograms are a little harder to compare because we have an outlier in GR1 all the way down there to 0. So I don't think you see the granular distribution that you do in GR2. But if you did, you'd see the shape is relatively the same. So the good news is that we have a mean and a median in the mid 70s there. The less great news is that we have that, this is to use terminology from our own course, we have very left skewed data here, right? And so we have this trailing tail out of people getting into the 30s, 40s, and 50s that I know is not where you guys want to be, especially on this last GR that we took. So I've already set up with some people of talking about meeting up this week. Hopefully today or tomorrow I can release that GR so you guys can look at it on your own. But I highly recommend that if there's anything you're curious about, you set up a meeting with me and we can go through the GR question by question to see what mistakes you guys made, whether or not they were just silly mistakes, whether or not there's something that you just need to read more carefully, or whether there's something more fundamental, or heaven forbid, that there's something that the question was either was stated in a way that perhaps two answers were correct. I do my absolute best to catch those ahead of time, but I acknowledge that it could happen. So if you find a situation like that, please let me know and I will look into it, because nothing would bring me more joy than getting to legitimately give you guys back points on an exam. I just have to actually find it and have to be legitimate. So please don't shy away from bringing those up to me. From a admin point of view, as a reminder, we've got homeworks 27 and 28 are coming up due next Tuesday, along with lab 8, and I would recommend working on that earlier rather than later. I'm going to try to set aside time so that we can work on Wednesday largely on that because it's an extension of our lesson today. However, I think that's pretty much where we're at. I was trailed off there. I thought I had some other big point, but apparently I don't. Does anyone, before we get into today's stuff, does anyone have any questions on anything I've said or that I didn't say or that was coming up or that's happened? What do you guys got? All right. Okay. So we are getting into block 3, which block 3, if you looked at the syllabus, is about regression, right? Which is something that, like I said in the guided lesson, most of you guys have seen or had some experience with, even if you don't realize it, right? Because regression is basically building models. It's basically, we've up until this point have been doing things like hypothesis tests where we're saying, you know, is this true? Regression is taking the next step and saying, can we take the data and build a model so that I can then predict what a value is going to be without having the data for it exactly, right? And so there are entire classes on modeling. And we're not going to get deep into all of that, but we are going to look at block 3, one particular type of modeling, which is linear regression, right? Which again is probably something you guys have seen, where it's basically I have a bunch of data and I realize that it is related in some way, and I try to build a line to model that data so that then I can say, I think that as this variable changes in a particular way, or we'll look at multiple variables. But the point is that we will be able to, given some data, predict what another variable is based on a linear relationship between those. But before we get into that, we are going to talk about ANOVA today, which ANOVA is kind of, think of it as it's an intro to some of the things we're going to be doing in this block from a programmatic standpoint, because we're going to be building these tables and pulling out values and whatnot. But conceptually, it's kind of a capstone to what we did in block 2 with means, right? Because we ended block 2 talking about looking at means. So first we said, what about a single mean? Like, is the average height at USAFA 70 inches? Then we looked at a difference of means, saying, is there a difference between the average height of USAFA cadets and the average height of West Point cadets, right? And that kind of mirrored what we did earlier in the semester with proportions, right? Because when we had proportions, we could say things like, is the proportion of engineering degrees equal to 25%? And then we could say, is there a difference in the proportion of cadets with engineering degrees at USAFA compared to the proportion of cadets with engineering degrees at West Point, right? Well, then we introduced in the middle of the block this idea of a goodness of fit, right? And the goodness of fit was really comparing several proportions at the same time, right? When we said in the lab 6, when we said, hey, is the proportion of cadets in each one of the divisions equal, we were really saying, looking at several proportions all at the same time, right? And that's what analysis of variance is for means. We use, it's a technique to check if the means across many populations are equal. So in a nutshell, it's for saying, whereas before I might say, what's the average height of USAFA cadets? Or I might say, is there a difference between the average height of USAFA cadets and West Point cadets? ANOVA would be to say, is the average height of cadets the same across all service academies, meaning average USAFA height equals average West Point height equals average Naval Academy height, and so on, right? And so it is a technique we use variance to compare the means across multiple populations. And the alternative hypothesis is simply that the null is not true, right? So the alternative is not that they are all different. The alternative is just that at least one is different, okay? And so the important thing that I want to foot stomp at this point is simply that we call it analysis of variance because we use variance to compare the means. We are not comparing variance, we are comparing means. That's what the null is, but we are using variance to do that, right? And I just always kind of put down here at the end that, restate that other way, that we never use it to test for differences in variance, because that will come up later on a test almost for sure. And one of you guys, no matter how many times I say this, is going to break my heart and say, oh no, analysis for variance, that's when we are trying to see if there is a difference in the variance. No, we're using that as a tool to check the means, right? And we'll get into the math of it a little bit more, but really the way we look at it is, like, assume these are 3 different populations, A, B, and C. I don't know, make A USAFA, B West Point, C the Naval Academy if you want. And when we look at it, we say, hey, when I look at each of those, I can see that the mean is different in each one. Now, don't forget, in a box plot, that little white line, that's not the mean, that's the median. But even so, you can see that the mean of the data is slightly different. The data is shifted, right? But we use the variance to compare it, because when we look over here on this first box plot, I say, yes, the averages are different, but there's such a big variance or variation in the data. I can't tell if the real means are different or that the sample means are just different. But since my sample varies so much, maybe if I took another sample, they would be the same, right? Whereas over here on this one, I have the same means, but I have a much smaller variation. And because of that, I can be more confident in the fact that yes, the means are different because my sample means are different. And I have such small variation that I can be more confident that that actually is representative of the population, that the means are actually different. That's a very hand-wavy, non-mathy way of kind of hitting the big points, but I want to kind of describe where we're going before we look at it. So before we dive into the actual like prepare, check, calculate, conclude process here, do you guys have any overall questions about what's going on here and what these null and alternative hypotheses that we're testing here, if you want to say mean, but I'm trying to avoid using the word mean if possible. So what do you guys got, if anything, on questions here? Okay. Interrupt me if you do think of something. Okay, we are going to run through this. I'm going to throw an example on you guys, and we are going to run through this with the same PCCC process that we've had throughout the entire block 2, just with slightly different steps or not even different steps, just different parts of those steps for what we're doing. So we're going to start with the prepare step. And I was going to say, I should actually give you guys, like before, have prepared a associated RMD file, and I was going to give it to you guys afterwards, but there's no reason for me not to give it to you right now. So I'm just dropping it in the chat right now. If you look over there, you can see the code that this is based on if you want to follow along. Now, if you want to actually run the code uses the cadet GPA data that you've been using for the past labs. So you would have to just edit, I think it's around line 27, the line that brings in the data, because right now that data is linking to, that code is linking to my computer, which hopefully you guys don't have access to my computer. So change it to where you store it. Okay. So let's go through this. So for the prepare, first we have to define our parameters. And this is a part that I really encourage you guys to take a little more formal than you have in the past, because when I talk about defining the parameters, I mean giving them specific names and describing what they are. So in this case, my overall question is the average GPA the same across all divisions at USAFA? And so I can just state it that way, but to be more specific, I want to say, let mu sub div be the average GPA for a given division, because once I have that definition, then I can more easily formally state my hypotheses, right? So if that's what mu div means, then the null hypothesis is that mu for engineering equals mu for basic science equals mu for humanities equals mu for social science, right? And then my alternative is simply that at least one is not equal. Or you could write that as the alternative is that H naught is not true, right? I could write it mathematically, but that would just be a little more lengthy, because I would have to write that mu engineering not equal mu basic science, or mu engineering not equal mu humanities, or mu engineering not equal mu social science, or mu basic science not equal that, or mu equal, or mu not equal that, right? So I have, if I do it that way, I have a lot of things I have to write out. So it is just easier to explain it in words there. Then I got to set my significance level, because we've said before with hypothesis tests that we've got a lot of different hypothesis tests for testing different things, but they all start and end the same way, right? They all start with a set of hypotheses and a significance level. Then we do a bunch of analysis to test those, and we end with a p-value. And we take that p-value and compare it to our alpha. And if the p-value is smaller than alpha, we reject the null hypothesis. If the p-value is bigger than alpha, then we fail to reject the null hypothesis. All right, then we have to collect and analyze some samples, right? And so in this case, because I am comparing several different populations, right? Because when I say, is the average GPA the same across all divisions at USAFA, I am talking about 4 different populations: the engineering cadets, the basic science, the humanities, and the social sciences. And so when I collect these test statistics for each one, that is not saying that there are 80 total engineering cadets. It just means I have a sample of 80 engineering cadets, and that of those 80, the sample mean GPA is 3.1648, right? So I am collecting these sample statistics on each one of the groups. Now I only have 4 here because the groups I'm interested in are divisions. I could have easily asked a question like, is the average height for people the same in every country, right? And if I did that, then each group would be a country, and I'd have 300 or so different groups. But I would still have to have the sample size, sample mean, and sample standard deviation for each one of those. All right, so that is all we need to do for the prep step. Any questions on generically what we're doing here? All right, well then we can move on to the check, which the check is going to be very similar to what we've seen recently, right? We still have to check, are the sample observations independent? Which if I didn't tell you here, but if I told you they come from a random sample, then you could say, yes, they are independent. Then we need to check, are the data in each group nearly normal, which same as we've done recently, the easiest way to do that is to look at the distributions and then based on their sizes, say, do they look mostly normal and do they have any clear or extreme outliers? Well, none of these have any outliers, let alone clear or extreme. This one, and this one all have sample sizes bigger than 30, and so they have no outliers and they don't look particularly not normal. This is the only one that has a sample size less than 30, but it has no clear outliers. So I'm good on that. I can still say that I passed my normality check, right? This is the new check step that we didn't have before, though. Is the variance in each group nearly equal? Because in order for me to do my comparisons, I need to be able to assume that within each group, the variation is about the same. Now, there are a lot of ways you could mathematically test this. We're not going to get too in the weeds on this. For your guys' purposes, when you were doing this check step to say, is the variance of each group nearly equal? All I'm going to ask is that you look at the IQR, the interquartile range, right? That is the height of each one of these blue boxes. And as long as you look at all of those blue boxes, those interquartile ranges, and say they are about the same height, we are going to say that the variance in each group is nearly equal, meaning the interquartile range is spread out about the same for each one. Therefore, we can say that they are nearly equal. Now, this is definitely a kind of rule of thumb type check. So it's totally reasonable that someone else might look at this data and say, and someone else being one of you guys, you might say, hey, well, this is that high, and this one has this extra height right here. And so I think social science actually has a meaningfully larger spread than humanities. That's totally fine. And you can put that into your results. We're still going to do the check either way. Remember, we never can say for most cases whether something is 100% passes or 100% fails. We're just showing that we did our due diligence and giving our call on it. So you would be equally reasonable. It would be equally reasonable if you were to say, do these box plots and then say, looking at the IQR, they all look about the same, so we can say that this step is met. Or you could say the IQR for social science seems slightly larger than humanities. This might be something we want to keep an eye on later for our results. Either one of those are fine, but as long as you're showing that you've done your due diligence and you've made a call and why, then you are good to move forward on there. All right, before we move into calculate, how are you guys feeling about check? Excellent. All right. So calculate is actually going to be one of our easier steps here. Because I've said in the guided lesson, the upside of this block is that R is going to do a lot of the heavy lifting with a single line of code. The trade-off is going to be that it is going to, with a single line of code, give you a bunch of information. And so it is going to be more important that you understand how to interpret it. As we move forward in technology and society, this is a trend you guys are going to see more and more, is that technology and computers are going to do more and more for you. And that means it is going to become more and more your job to interpret it, because that is the one thing that computers are still very much lacking in being able to do. So one of the things you're going to have to do is calculate the degrees of freedom. Now, I say you're going to have to calculate the degrees of freedom. R is actually going to do it for you, but I need you to understand where it is coming from, because you're going to have 2 degrees of freedom, because our test statistic is going to end up being a fraction with a numerator and a denominator. And the numerator is going to have to do with the groups that we have, right? How many, and so the degrees of freedom for the numerator is going to depend on how many groups we're comparing. In our case, we are comparing 4 divisions. So we have 4 total groups. And so the numerator degrees of freedom is going to be 4 minus 1 is 3. If we were comparing, like I said before, average heights between all countries, then I would have like 300 groups and thus 299 degrees of freedom. And so the point is the number of groups I'm comparing is important, has to be accounted for, because that impacts my analysis. Similarly, the other thing that impacts my analysis is how many observations I took total. If we go back to here, this right here, adding all of those up, those are the total observations I have across all of my samples. And so the 2 things that are going to affect my analysis are how many groups I'm comparing and how many total observations I have between all of those groups, right? So those are going to be my 2, that's where my 2 degrees of freedom are going to come from. And then I'm going to calculate my ANOVA table. Actually, I'm going to calculate that first. My degrees of freedom are going to be in there. But with a single line of code, I'm going to spit out this one-stop shopping of everything that I need, right? And so that's what this is, and you can see the degrees of freedom are right there in the first column. And some of these columns may not mean as much right now, but that's what we're going to spend our time on today, and to a lesser extent tomorrow. And so the big things that you need are this right here. That's your test statistic, right? It's an F value, but it's just because it's a new test. When we first introduced proportions, we had Z values or Z scores. Then we introduced chi-squared. Then we introduced T. Well, now we are introducing F. And so this is our test statistic. It's our F value, right? But more importantly, that F value gets that P value, right? It says the column heading PR, probability of getting a value greater than F, because that's what the P value is. Because the F distribution is a little bit like the chi-squared distribution. We always only care about the upper tail, right? And so that's what our P value is. And so once you have that table, you don't have to memorize any other functions. You just have to have that table and know how to pull out what values, because then your conclude step is basically just going to be, hey, our F value is 5.63. That returns the P value of 0.0009. That's smaller than the alpha we agreed upon early on. Therefore, there is statistically significant evidence that the average GPA is not the same across all divisions, meaning we reject the null hypothesis, because we're basically saying if the null was true, there is a 0.0009 probability that we would get these results. Therefore, we think it's unlikely that H naught is true, right? To give you an idea of what's kind of happening under the hood, and we're going to get deeper into the math tomorrow, but this is what a F distribution looks like, right? And the F distribution is while the overall shape stays the same, it's these degrees of freedom that decide how squished up it is, right? As I change the number of groups I have and the number of observations, this might look something more like this, or it might look something more like this, right? It depends on how spread out and how squished to the left it is, right? But both of those have an impact because, and then once I have my test statistic, this test statistic, which is this value here, is this number divided by this number. The top number there is the what's called the MSG, the mean squares of the group, right? Without getting into the deep math, it is a measure of how much variation there is between the different groups, in this case, between the different divisions. Whereas the denominator is the mean standard error. This is how much variation there is within the groups, right? And if the mean was really the same for every single group, I would expect there to be the same amount of variation in the groups and between the groups, meaning that that F should be 1, right? So if the means really were the same, I would expect to get a value around here. And if I got that, I would get an F value of 1, and my P value would be something like almost 50%, and I would definitely not reject the null hypothesis. However, in our case, we got 5.63, right, which is way over here. And so this probability that you can't even see over there is that super small probability that we got, right? And so that's really, in a kind of hand wavy fashion, where this F value is coming from and how we are calculating. We're going to talk tomorrow, or I say tomorrow, you know what I mean, Wednesday, more about what these numbers represent and where they come from. But I'm more concerned that you are able to generate this table and interpret that value to make your conclusion on that. All right. Before we switch gears and look at the code a little bit, does anyone have any questions about the general PCCC steps here that we went through and what our ultimate conclusion actually means? For the record, I have a water dispenser over here when you guys see me turn to the side and hear that sound. Okay, then let's do this. Let's take a shift and move over to this code. So I'm gonna, if you haven't done so already, I'm gonna give you guys about 5 minutes. Download that R file that I posted up there, and then see if you can edit this line right here to make sure that it is pointing towards bringing in the GPA file that you guys already have. And if you run into any problems, let me know and I will help deal with that. But I will mute for a second while you guys do that. All right, Ryan, did you have a question?
Yes, sir. I was looking at line 60 in size, and it wasn't running. It doesn't look like in size was ever stored in the above
Well,
variable.
it should be at line 50,
Okay.
where n size gets aggregate. So maybe it was not run correctly, or is that not there? Or are we talking about something different?
It's there.
Is it did the block above it get run?
I see what it's doing. It's I think I got it fixed.
No worries. Like I said, you guys would, well, I'd say you'd be surprised, but maybe based on your guys' work with computers, you wouldn't be surprised. But I would say of the 3 years I spent on my PhD, at least 1 year was me spent just looking for semicolons or letters that were capital instead of lowercase to get my code to run. I wish that all my time was spent making humanity better, but a large portion of it was just finding errors like that. All right. Any other question? I thought I heard a mic pop on
Yes,
for a
sir.
second.
I have a question. Could you actually run that like code chunk where n size, x bar, and SD are like aggregated?
This one right here.
Yes, sir.
So yeah, I
Okay.
just run it. It doesn't actually output anything. It just stores them.
So mine is throwing an error at that, but I guess I don't know. That
What's
might be.
what's the
It
error it's
says
throwing?
so when it tries to do SD, it says basically it says the object fun of mode function was not found. Um,
So a couple of quick questions to make sure it's not something easy. In line 27, did you name your data file cadet?
yes, sir.
Okay, because that's down here is what it is pulling it in. And then when you are running this, would you mind sharing your screen so I can look at, see what the error is, see if it's something I recognize?
Yeah, I can do that real quick.
Is anyone else having trouble with that, same type of trouble with that block? All right,
Can you
so
see this?
I can. Let's take a look. So I am looking. So you ran that, and then you ran that. Okay, let me see. The and object. Why doesn't it like that? Object fun.
Sir, I think I might have the wrong path. Let me, because this is the path from like what I had for Lab 7, so I think it's not able to read it.
Gotcha.
So that might be the issue.
Okay, take a look at that and let me know. It looks like you've got variables over there. I would, yeah. So try running everything at once and see if that does it in order. If it's maybe being a run in order issue. All right, I'm going to reshare mine. I'll come back to you and let me know if you have better success. But let me run through what this is doing, at least intending to do, and then we will deal with anyone who's having issues on this. Because in theory, what we're doing here is a lot of this should be familiar, but here we're bringing in the data and setting the variables to different types. Then we're setting our alpha. This section that we've been talking about here is where we are collecting the statistics, right? And so one of the issues that makes this, I did this in a way that I felt was simpler, but if you find it annoying, you can do it one at a time. Because basically what I'm doing is I am finding the sample size for each sample all at once. And the same thing with X bars and the standard deviation, because I'm saying, hey, for my sample size, I'm using the aggregate function that we learned way back at the beginning of the class and said, hey, aggregate, look at the GPA variable by division in the cadet data set and apply the function nrow, which is counting the number of rows. So it's basically going to say, count the number of rows for each division. Down here, the function is mean for x bar, which means find the mean of the GPAs for each division. And then same thing for here, function equals SD, find the standard deviation for each one. So that when I run, when I see what does n size look like, I get this, which is a for each division, how many are there in each one, right? If I, instead of saying show me n size, I said show me x bar, it would be the same thing, but it's going to be showing the average for each one of those, right? And so you definitely don't have to do it this way. You could do each one individually. I just think this is much faster, especially if we are doing more than 4 groups at a time. If we start doing things like comparing all 300 or so countries, it can be painstaking to do that one at a time. Again, that's the other reason this block here, you do not need to do or even understand this block if you don't want to. This is just a way to pretty it up to look at it all at once. I'm basically saying, hey, take all those sample sizes, take all those means, take all those standard deviations, and stuff them into a matrix called CStats, and then give the rows names and the columns names. And by doing that, I can get this little prettier way of showing, hey, here is that table, kind of like we saw in the presentation of each of my statistics for each of my groups. So again, you do not have to do this. You can do it manually for each one, but I find this to be a convenient and easy to understand way of putting it together. Then we get into the prepare step. Are they independent? I said it's a random sample, so it is. Are they the data relatively normal? Easiest way to do this, like we've seen before, is to make these distributions and look at them and say, hey, all the sample sizes are bigger than 30 except for the humanities, but it doesn't really matter because there's no clear or extreme outliers in any of these, and none of these look particularly not normal, so I'm good to go. This is the new check step we have, right? Is the variance about equal? And so we're going to do this, say a box plot of the GPA by the division, right? And that gives us this number, which you're equally, as long as you're doing the due diligence here, you can say, you know, look at that and say, yeah, that looks about normal, or it looks about equal. You would be within your rights to say, oh no, you know what, social science looks like it has a larger IQR, interquartile range, that blue box, than the other ones. We should be a little concerned about that. Either one of those is a fine explanation as long as you do the work and make the call. All right, this right here is the money line, right? This right here, summary, AOV, cadet GPA, that is saying AOV is analysis of variance. So this is the line that is doing the analysis of variance, right? When I run this line of code, it is going to spit out that table. Now, you don't need to do this A table. That was me just storing that information into a variable so I could access it later. I could just run the summary and it'll still give me the table. Now, the summary part is important, right? Because if I take off the summary part and delete that and run, it will still do an analysis of variance, but it won't summarize it for me. So if I do AOV, it goes, cool, I'll do the analysis of variance. And then it just spits out the degrees of freedom and the sum of squares, because that's what it thinks was important and proves that it did it, but it's not giving you all the stuff that you want. So you want to put in that summary function to say, hey, I want that full table, because that's going to have the values that you need, most specifically that p value, right? And then you don't need to necessarily do this. I just did that because I wanted to store this table in case I wanted to use it later. This last line right here is interesting. These are significance codes, right? So what these are is, these are little things that are saying, up here it's going to show you results. And so the fact that it has 3 asterisks here means that it is saying, hey, this is significant if your alpha was 0.001, then this would be a significant result, right? We had an alpha of 0.05, and so that's a 1 star. So anything more than 1 star, we have 3 stars. So it's saying, hey, yeah, it's definitely significant for that. It's somewhat trivial when we're only looking at 1. You can just look at this number, but you can, we'll do situations where there are more lines here, and we'll talk about that later. And so then it becomes kind of handy to have that visual, like, oh, that's significant. That's not, that's significant. But that's all that is right there. Now, this is all you need to do, because like I said, this is the one-stop shop. So by doing that, I could say, hey, my p-value is that. That's less than the alpha I chose. Therefore, I have significant evidence to reject the null hypothesis. This little conclude part of code here, you do not need to do or understand. Again, this is just something where I had some questions people wanted to see, and this is how I share it. And so this is showing how, if I store that table in a variable, how I could access the things directly, right? And you don't have to write all that out. You can say a table, and then if I say double bracket 1, that accesses the table. And then I can say $, and then I have all the parts of that table I can access just like I did before. That is not something you need to understand. That is just kind of an advanced method for some of you guys who are getting more handy with R and want to be able to print out your stuff more easy for you to read. Then look at that and understand it and ask me questions about it. If not, don't worry about it. I am more concerned that you are able to create and understand this table to draw your conclusions, because this conclusion at the end here would be the same regardless of whether or not we had that written out there. All right, that is the big ta-da moment of ANOVA. We're going to go Wednesday, into a little bit more of what each one of these numbers means and where they come from and whether or not we might use it or care about it. But right now, I am more interested that you are able to set this up and do it, because this is the heart of Lab 8. And so I'm going to try to set up Wednesday as much as possible that we can have as much class time as possible to work on Lab 8 during class. So I highly suggest that if I go, where am I? If I go to, I just realized you guys can't see this. So this is if I go into the class materials here and then go into the labs, Lab 8 is now posted up there. And I would highly recommend start working through the guided portion and read through the on your own, so that you can bring those, rather than taking all of Wednesday's class, figuring out what questions you have, figure out what questions you have first, so that we can spend Wednesday's class working on it. And so I would actually ask that for the last few minutes that we have here, that you guys go ahead and get into the files here and download these files, so that you guys definitely have them and can start looking at them now. So while you are doing that, let me jump back to Zane. Zane, did you get any further progress on your error, or are you still having the same error?
I got it to work. I cleared the variables and then it worked. So maybe I had like something named, like some name conflict from earlier, because I hadn't cleared it since last week.
And that brings up a great point. If you ever run into a error that you don't know what's going on, I highly recommend that the first thing you do is clear your variables, because if you at some point used a variable name the same as I did, which is possible because if you're running my code and you just never clear your variables, I tend to use similar variable names up there. If it's a different type, it might have an error like that, where it's basically saying, hey, this variable is a word, you're trying to assign a number to it, or this is a number and you're trying to assign a list of numbers to it. It's going to have a heart attack. And so by clearing that out, you take that out as a problem. And then you might still have errors, but then we can deal with what they are rather than, phantom errors on that. I will say also, as I'm looking at this lab here, from past experience, I will say one of the technical places that cadets tend to get stuck is on this concept of stacking the data. So I highly encourage you to read through and make sure you understand how to, what stacking data means and how to do it. And if you have any problems, bring that on Wednesday. But that is something that you can do in R to facilitate ANOVA, but it is not part of ANOVA, but it is important that you understand how to do it. It's almost like importing the data. It's an important part of the process, but not one that is explicitly taught in the book because it's specific to R. So make sure you read through and understand the example so that you can use it as necessary. Sometimes it is, sometimes it isn't, but it's a tool you need to have in your box. Okay, we are about 3 minutes out. And so I am going to, unless anyone has any questions, I will stick around, but you guys are free to go and take a 2-minute power nap here before your next class. I will see you on Wednesday, if not earlier. Like I said, I'm going to focus on trying to give you as much time on the lab on Wednesday as possible. So take some time to take a look at it so that we can use that time to actually clear up any questions you guys have. And then if you do have any lingering questions on the GR, make sure you set up those times and I will be happy to go over with you guys this week. But otherwise, I will stick out for a couple of minutes. But if you don't have any questions, I will see you on Wednesday, if not earlier than that. So do your best. Have a great week. I'm going to try.